Hi, my name is Łukasz, and today I will talk about connections and finite element analysis. We will talk about what is important, FEA modeling basics, modeling of bolted connections, example of connection strengthening, and a summary. I will try to wrap this up in 20 minutes, so I assume that you kind of have a little bit of basics in FEA, so we don't have to touch on those. So firstly, let's talk about what is important. When you think about connection and capacity of the connection, especially a connection that you wish to strengthen, the first thing that comes to mind is the capacity of the connection. Something can break, yield, tear, and so on. This is like the natural thing that we consider when it comes to connection capacity. However, we cannot forget about connection rigidity. It's important, especially since when you are strengthening the connection, and it's very likely that you will also increase the rigidity of the connection along the way. It's relatively difficult, if not impossible, to strengthen the connection in such a way not to increase its rigidity. Of course, with increased rigidity, the connection starts to transfer higher and higher bending moment. Of course, you can strengthen it in a way to make it possible for the connection to transfer the moment. The problem is that after the connection, there are other elements of your structure. So it would be stupid to strengthen the connection, increasing its rigidity so much that later on something else fails because the connection that was strengthened simply started to transfer higher bending moment that other elements can consider. Also, it's worth remembering about the impact of connection rigidity on stability. Here, at least the saving grace is that as you strengthen the connections, usually the stability gets better, so nobody loses. It's like a net benefit. Although it's a topic that is rarely talked about, so I figured I will mention it here. Of course, during a presentation, I have only a space to talk about one specific thing, and quite obviously I've selected the capacity because, this is the most obvious and most reasonable thing. However, I don't want you to think that other two things are less important. It's not like this. Since I want you to learn about those other things as well, I've recorded a special video lecture. You can sign up to using the link below this video and simply learn about connection rigidity and other things that I will discuss in this training. But for now, let's focus on capacity. When you look at this, you can say, hey, wait a second, this is a simple pinned connection. Every engineer understands that there is a code that will allow you to calculate the capacity on such a pinned connection. And as such, it may seem that only weirdos and scientists would be calculating such simple pinned connections using FEA. And for the purpose of this presentation, let's assume that weirdos and scientists are two completely different groups of people. However, this is true only to a certain extent. Imagine that you have an element like this, and it fits between two plates, so you cannot add external plates, and realistically, the only way you can strengthen it is to drill a bigger hole and weld the tube inside. And you hope that this tube somehow will take at least a little bit of bearing stress and transfer it to the other end of the opening. And this is how you wish to strengthen the connection. There are no code rules for that, and in such a case, FEA is your only friend. Similarly, you can have problems with low cycle fatigue, and in this case you might want to have a very accurate model to calculate where stresses are, how they increase, and so on. However, usually when we talk about steel structures, you think about beam structure like this one, and of course somewhere there is a connection that you may wish to calculate or strengthen. And while I love using FEA, I am not here to convert you or to tell you that every connection has to be calculated with FEA. That's absolutely not the case. So if you have a simple connection, you can calculate according to the code of your choice, be it Eurocode or something else, by all means do. And even if you have to strengthen such a connection by adding a bolt, you can just calculate this strengthened connection by the code as well. Heck, if this won't work, you can even weld the connection on site and This is also relatively easy to calculate. Just remember that if you are using bolts and welds together, according to Eurocode in chapter 393, it says that basically you can't add up the connection of the weld and bolts. I mean, there is a workaround where you tighten the bolts but not pre-stress them. You then do the weld and then you pre-stress the bolts, and this would allow you to add the capacity of bolts and welds according to Eurocode. However, realistically speaking, when we are talking about existing structures and strengthening of the connections that already exist, the pre-tensioning already happened, so there is no space to actually do that. With that being said, let's take a look on FEA modeling basics. The first choice you will encounter is which type of elements you should use. I mean, if I tell you that we want to model the connections in FEA, the first thing that will come to your mind most likely is such a solid model. But you also can use plates or beam elements. And while solid models look great, I will highly encourage you to use plates. I feel that solid elements are greatly overused in modeling, which leads to a lot of issues later on, and I would definitely encourage you to use plates, which are just as accurate, if not more, and allow you for a certain freedom in modeling that will really help you out. Of course, plates alone won't make it, because most of the time you will be dealing with models made of beams. So this has to be some sort of a connection of plate model and beam model. There are essentially two approaches you might have to this. The first one is if you have a huge structure and you want to calculate only a small portion of it, you can make a separate model completely out of plate elements of the node that you wish to analyze. Then, of course, your model floats in air because you don't have the rest of the structure in it. So the best solution would be to simply support one of the beams as a rigid support, and then use the loads from your static model, the forces in each member, as active loads on each other beam. Of course, the hope is that your node is in equilibrium, which means that in this one beam where you used the support, you hope that the reaction forces will be equal to the values of forces in your static model, and then you will be certain that you represented the situation of the node nicely. And as such, you can calculate such a cutaway model separately. This would work, but if you would have a lot of load combinations, it will be a huge hassle to transfer all the loads into your model. This is where is modeling a beam structure and simply cutting away portion of it to create a plate model of a connection within the beam structure might be much better choice. Then you don't have to worry about fake boundary conditions and you don't have to transfer anything manually because your model would calculate everything for you. Of course, in such a case, I would advise you, especially if you have a big model, only to add one or two plated connections in a model, and if you have, for some reason, several connections that you wish to analyze, then I would advise to use several different models. You don't want to end up with a huge model that you won't be able to compute in your calculations. So, how to then model it? You will encounter one problem, and that is how to connect plated elements to beam elements. There are two options. You can either fill your plated cross-section with infinitely rigid stiffener, and then the central node of this stiffener will be the node where the beam element will be connected to. Or you can use a rigid body element, so rigidly connect all the nodes on the circumference of the plated cross-section to one node on the center of gravity of the cross-section where the beam element will be connected. And this way you can make a smooth transition between the plate elements and beam elements, which makes the model work. Of course, you should also think about material model. When you are modeling connections, most likely there will be plenty of stress peaks And you don't really want to analyze how many times stress can be higher than yield for this to work. You want to have a solid, concrete answer. And with that, it's very beneficial to use nonlinear material properties. Eurocode and other codes allow you to use very complex material models, as you can see at the bottom, but I strongly feel that a simple bilinear material model that simply is linearly elastic up to the yield and then perfectly plastic horizontal line till infinity is absolutely sufficient when it comes to modeling connections, especially made from normal structural steel that have like a easily seen plastic plateau. So I would highly advise you to use this particular solution. In the end, one of the biggest issues in connections and in modeling would be contacts. After all, in bolted connections, you have plates that touch one another and can go inside one another, but they are not really attached. So to model that, you either use contacts or gap elements. Contacts are nice, but not all FEA programs used contacts, have the ability to do that, but also some of those are not simple to use, might be difficult to converge, and so on. So if you have issues using contact, you can use gap elements. Those are simple elements that transfer compression while they do not transfer tension. And essentially, if you connect all the nodes of one plate with the nodes from corresponding nodes in the other plate with compression-only elements, you essentially faked contact, and that is a nice approach to it. And I did several models that way before I had solver that actually used contact. But all of this is nice, although we haven't yet touched on the most important part, and that is how to include bolts in your model. After all, you can model a connection, but if this is a bolted connection, you need to have an approach to modeling bolts themselves. And there are two options. The first one, easier one, is best when you have a connection that will have bolts in tension. This can be, for instance, in such a end plate connection when the beam is in tension. And in such a case, when bolts are in tension, they can fail due to bolt failure in tension, punch through the plate. Although I have to say that in industrial applications, plates are usually so thick that this will not happen, so it's not a big deal. It's easy to calculate though, but it's good to be aware of it. Although if you are using cold formed elements and so on, this will become an issue. And then the end plates themselves can fail due to stress state in the end plates. You will notice that I marked the bolt failure and punch through in blue on the left. This is because to calculate that, you only need to know the tensile force in a bolt. In some sense, it doesn't matter how you model the bolt. It can be as simple as simply connecting two nodes in the end plates with a beam, and FEA will calculate the tensile force in a bolt correctly for you. However, if you want to check the capacity of the end plate in green, it's not as simple. If you would connect the plates simply catching by a single node the beam element, the problem is that the stress peak there would be so high that it would seem that your plate failed. So you need to have a solution that has a reliable way of distributing stress around the circumference of the bolt in a more reasonable way. And to do that, you can model the bolts like this. Imagine that you have a bolt in a connection between two plates. Of course, those plates will be meshed using plate elements, but you want to leave the opening for the bolts empty. Usually your CAD geometry comes with bolt openings already introduced, so just leave those, and this will allow you to use this approach easier, although adding the opening with a bolt diameter will be a reasonable solution as well. This will, of course, be modeled with plate elements, 2D elements. And when you do this, the next step will be to fill the openings with rigid body elements. You simply put infinitely rigid elements inside, and then both of those rigid elements have the central node. You will connect those central nodes with a beam element. The beam can have a diameter of the bolt, of course. This is not yet the end, you still need to have a contact or gap elements between the plates to mimic contact. And when you model your bolts this way, they will be able to nicely transfer the tensile force around the circumference of the opening to have a reasonable stress distribution. The bigger problem will be when you have connections in shear, like this one here. Bolts in such connections can fail in shear and sometimes in bending, although in reality, bending of the bolts, if the plates touch one another, is usually omitted in design. It would actually happen if you would have like an actual air gap or maybe some sort of non-constructional material between the plates, like a seal of some sort. Then it would be a bigger issue. Then you have the bearing contact stress, contact capacity of the plate, block failure of your plates, and also the failure of the cross-section weakened by openings. And in Eurocode terms, the last one would actually be the capacity of the cross-section, but I prefer to think about it as a capacity of the connection, simply because it happens only near the connections. So I will take it into account here. And again, the ones on the left in blue simply require a decent force value in the bolt, so any bolt modeling technique would work, but those in green actually require a reasonable shear distribution. Note that reasonable shear distribution around the circumference of the opening is not uniform distribution. So our previous model that used rigid body element inside would not work because it would throw the a shear around the entire opening. This is not what we want. We want the bolt to touch on the side where the shear happens, and on the other side there is no stress. To achieve that, we will slightly modify our model. We will use the plate elements with the openings as previously, but we will fill the holes instead of rigid body elements with gap elements that simply transfer compression. When we add the bolt, this will nicely transfer shear. Of course, the compression-only elements on the side where the shear happens, where the contact should happen between the bolt and the plate, will transfer the stress. On the other hand, on the other side, those elements will be in tension, so they won't transfer anything. This model works. Sadly, it is unstable because such a model can't transfer tensile forces. So to make it work, we will extend the bolt and add washers. Washers consist of a bit of plate elements and rigid body elements. So we have something attached to the washer, and then as we defined the contact between the plates and also the contact between the washer and the plate, this thing suddenly becomes stable. It's stable because as the tension comes, the washer pushes on the first plate pushes on the other plate pushes on the other washer, and suddenly our bolt can transfer tension while maintaining a reasonable shear stress distribution around the circumference of the opening. The problem is that we have something I call the sandwich of contacts. We have a plate on a plate on a plate on a plate. So there are 3 layers of contact that have to converge one after another. So sometimes it's irritating. Without a doubt, it's easier to use and converge analysis with the first model, but sometimes you simply have to use the second one. Regardless, so it's good to know that at least you have a way to do this. And finally, let's talk about example of connection strength. I've selected such a geometry, and I did it on purpose. Under around 1,500 kilonewton meters, you can see the the force distribution in bolts. This is a tensile force, of course. However, I would much rather use a chart like this because it nicely shows the strength distribution in relation to height of the cross-section. Eurocode would like this to be a perfectly linear distribution. As you can see, it's not the case, and this is why I selected this example. Simply put, the assumption in Eurocode that forces in bolts are distributed linearly is quite optimistic. And even if you would be unaware of this, FEA will allow you to notice that something is off. And this is one of the great benefits of using finite element in analysis. It can show you something you are unaware of, and that's great. Imagine that we are not happy that the capacity is only 1,500 kilonewton meters and we want to strengthen it. To strengthen it, we want to add a few bolts and a stiffener simply to make those bolts to cooperate better. Of course, you can see, hey, wait a minute, there is something off. The stiffener goes from the end plate literally to nowhere. We would like to transfer the tension from the bolts to the bottom flange, and this stiffener doesn't help with it. So I'm not sure if we should expect that this will be extremely effective. However, we still gain 18% of additional capacity, and you can see the tensile forces in the bolts here, and this is how the chart looks like. Even though we use the stiffener, it is still far away from the linear distribution Eurocode assumes. And also, you can see that this is not the most effective way of strengthening the connection. Sure, we managed to introduce another bolt, and some of the bolts had slightly higher tensile forces, but this is not the most efficient way. It would be better to simply connect the stiffener to the bottom flange. This way, the tension from the bolts have the way to reach the bottom flange where the tension should be, and this way we can hope that the connection will be better. As you can see, the capacity increase is 32%. It's nothing crazy, but, maybe it's enough. You can also note that the force distribution changed. The forces are more evenly spread, and you can see this also in a chart. Sure, it's still not perfectly linear, but at least it helps. Of course, the capacity of such a connection is not only forces in bolts, although that is a big part of it. We also should check the capacity of the end plate. As you can see here, the stress distribution in end plate does not really change all that much in calculations. You can see that at every load level, more or less the same amount of plate has yielded. However, this is just the value of yield stress. As you can see on the scale, it's 355 megapascals. So it doesn't really give us a good opinion on whether or not this is enough. Material yielded, but will that work? It's far better to use plastic strains to assess capacity. And you can see here that plastic strains in all of those cases aren't really high. Funny enough, Eurocode about connections does not give us any limit of plastic strains we could use. I think that the authors were simply not really trusting that people will do reasonable models of connections, and as such, FEA is not really mentioned in connection design. However, in our other Eurocodes, for instance, for shell or plated structures, usually values around 4-5% of plastic strains are accepted. And while in connections I perhaps would use a lower value just to take into account simplistic approach to modeling we had to use to make the model doable, I still think that the values we obtain, which is less than 1%, are absolutely fine. So, to wrap it up, let's think what is worth remembering. First of all, connections are not only about capacity, there is also rigidity, and this is why I recorded this additional 1-hour video. You can sign up to using the link below this video, and I highly encourage you to do so. Secondly, sure, you can use solid elements to model connections from time to time, but most likely you will not want to do this. After all, it takes a lot of time and effort, and it's way better to use 2D plate elements. Connections really like them, you should like them as well. It really helps to model the connections in a reasonable way, so I would highly encourage you to do so. Also, good to remember that if you're doing FEA, bolt intentions are usually okay. You can use the first, simpler model of calculating the connection, and that's fine. The shear connection, if you have to calculate bolts in shear and you really care about shear distribution in a plate because you're in a situation that this stress will add up to some other stresses in your model, then you will simply have to model it this way. I admit that the advanced model of bolt modeling is difficult and time-consuming, but, it's better than nothing, because at least it allows you to solve the problem that you may have. Also, it's a good habit to think how the force flows through the connection. And even if you don't have the experience to kind of feel it, FEA is nice because it shows you all those maps that simply show you where the stress flows through your structure, and that is a huge benefit. So using FEA can help you to gain certain insight and experience when it comes to flow of forces through structures. And this is something that really will help you in your engineering career. And in the end, FEA can calculate things you wouldn't be able to check otherwise. And it's a huge benefit and a very big value. Thanks to this fact, you can really benefit, as sometimes you simply encounter a problem that is outside of what is described in a code. And if you know Eurocodes well enough, you will know that it actually happens more often than you would think. So using FEA in those cases is great. And I definitely do not want to convince you to use FEA to calculate every connection. That's absolutely not the case. But when you are in need to calculate something and code simply does not allow you to do so, using FEA to calculate the capacity of such connections is a godsend, because FEA can literally calculate things that you wouldn't be able to otherwise. Thank you for watching. I really hope that you enjoyed it. Please remember to sign up for the free course using the link below this video. Have a lovely day.